Hey guys, I see we got 3 or 4 guys on right now. We'll give it another minute or so and we'll get started. All right, so looks like we got Chris, Ethan, and Toby, which is what I had planned for tonight was going through elementary circuits on for both series and parallel systems, which kind of seems like it might be a little elementary for you guys having an ex-Navy nuke, actually 2 ex-Navy nukes, and a senior NETA 2 guy that has gone through this. And so you're not going to hurt my feelings if you guys want to pass on this, or we could give it a couple more minutes, see if somebody else will join us. Maybe somebody's on by phone.
This is Toby. I'm cool waiting if we want to wait a few minutes, see if a few guys pop on.
Yeah, I'm cool with hanging on for a bit.
All right, sounds good.
If you hear screaming in the background, it's just the kids. Don't get weirded out.
Well, if you hear screaming in my background, it's probably my wife yelling at me. All right, well, we got Darren joined us. Welcome, Darren. Looks like we got Chris, Ethan, Toby. We're going to go through this real quick. I am recording this, so I'll probably still go through it, and we'll send it out to everybody, and hopefully somebody will be able to get some value out of this anyway. Again, this is probably going to be a little bit elementary for some of you, but I think it's going to be a lot of value for us as a whole. So I still want to go through with this. The intention for this 30-minute period was that what we've done in the past is we've gone through simple series and parallel circuits, gone through Ohm's law, gone through Kirchhoff, both voltage current laws, but the comment that I get back over and over again is that they still don't understand the circuits, or the biggest comment on failures on the NETA 2 exam have been that they've all been associated with Ohm's law, power equations, and to the like of that. So I want to mix it up a little bit. Instead of this being more of a one-way, I want this to be a little bit more interactive on Ohm's law and series parallel circuits. And so first of all, let me just say that for those of you that don't know, as you prepare for the NETA exam, if you don't know it already, a copy of the formula sheet that you'll get when you take the test, it can be found actually online. If you go to netaworld.org and you click under certifications and then formula sheet, this formula sheet is given to all NETA 1s, 2s, 3s, and 4s that are taking the test. What we'll be working on tonight is basically the DC circuits. So really only these two voltage equals IR, Ohm's law, and then the power equation, voltage or power equals current times voltage, will be of any value for you tonight. So you are expected to know a little bit more than that. So having said that, we'll go right into the first example here. And what we have is a series circuit with a power source, and we're given what the actual current is. So this might be a little awkward here, trying to get this set up here. Not sure why my screen changed there. Hold on one second. My screen changed and I don't know why. All right, so what we have is, doggone. All right, we have a series circuit. We have 24 volt supply and 2 amps. So what we don't know is what is our value of R3, is what's being asked of us. So the first thing that we have to do is try and figure out what is the total resistance that we need. So again, reviewing Ohm's law, voltage equals IR. So if we know what our voltage is, 24 volts, boy, this may not work here. Sorry, guys. So if we know that we've got 24 volts, trying to be all fancy here, that's going to equal our 2 amps times our resistance. But our resistance is part of the thing that we don't have. So if we divide that to find resistance, we know that we're going to have 24 volts divided by 2 amps, or a total of 12 ohms. So that's going to tell us our total resistance that we have. So now what we have to do is we have to pull back from one of our very first NETA at night and understand that resistors in series are simply added. So if we look at total resistance, that's going to equal R1 plus R2 plus all the way out to whatever our final resistor is. So in this case, we know that we've got 4 ohms plus 6 ohms is equal to, plus R3 is going to equal our 12 ohms. So just real quick math, we could see that R3 is equal to 2 ohms. And if we wanted to go back and check, we could simply go 12 ohms, which is what this would add up to. We could take 12 ohms divided by either the 24 volts, and we get our 2 ohms, or we could take work the Ohm's law in a different fashion, and again, just take current times our resistance. We'd have 2 times 12 would equal to 24 volts. So there's a lot there, on something that looks seemingly simple, but there's a lot to it that you have to understand that you're not going to get part of the equations. So here's another simple circuit. Again, we've got 24 volt source. This time they give us both of our resistances, and the question is, what is the total resistance of the circuit? Again, we have to pull back from what we had in the last equation and maybe one of the earlier NETA at night. So, hey Toby, do you want to try and do this one? I don't know if you're still online here. How about, who else do we have? Somebody want to take this one on? Ethan.
Sure, I'll do it.
All right.
Okay, so
I've
got pen and paper in front of me just because that makes it easier for me. So I take V equals IR for this formula. So I put the 24 volt source equals to the current would being 8 amps multiplied by and I do a parenthesis 1 plus 1.0 plus 2.0. So that's essentially it comes down to 3.00 ohms because you obviously add the 1 and 2 together, and then that's there's your formula.
Yeah, so yeah, you're exactly right. Or, maybe a better way is we know that we have a simple series circuit, so our resistance total is going to equal R1 plus R2. And so R1 was 1, R2 is 2, and so we know that our total resistance has got to be equal to 3. But you could do it your way as well. I think that we got to the same answer. But you had a very firm understanding of Ohm's law, and that's really good too. Now, another question that they could pull from this, and they don't ask this, but we could pull it in anyway, is, okay, well, if we now know that our current, we know our voltage, and we know our resistance, so what if the second part of this question was, what is our total power? What is our real power coming from this circuit?
And power is,
now again, this is it's up here, so power is equal to current times voltage.
okay, so it's just 8 by 24. So equals, let me do that real fast. So 192 watts.
192 watts. So that's another question that they can ask on you. If they ask anything, for example, is there any difference? What if this wasn't an AC source or a DC source? What if it was an AC source? Would it make any difference?
I don't think it would. But I don't know.
Fair enough. So yes and no. So when it comes to voltage, we have different kinds of voltages. We have voltage peak to peak, and that's where you're going to have a sine wave. And basically, it's the voltage from one peak to the next peak.
Yep.
So that's not what we use. So if, for example, they gave you voltage peak to peak and they gave you all these things, we would have to try and figure out how we would use this without doing that. What we would actually do is use something that's called voltage RMS. It stands for root mean square. So what that actually does is it gives you an equivalent. It gives you a DC equivalent of that voltage. And so that DC equivalent is really the same as what a DC voltage would be. It basically takes all these averages of your voltage on the plus and minus side, and it gives you a DC equivalent. So that voltage RMS, when it comes to this, is going to be the same as doing it with a DC circuit. And the reason why that is true is because what we're doing is we're taking one snapshot in time. So we're trying to figure out at this time, what is the actual voltage that we're trying to calculate there, or power, and that's why that works. So voltage RMS is what we want to do, and that's why when you look at your meters, your fluke meters that we hand out, that's why we give you flukes that will read in voltage RMS, and it's just the DC equivalent of that. To get to that DC equivalent, it's whatever your voltage is, peak to peak voltage, times 0.707, and that's going to give you your voltage RMS.
Okay.
So that's a very important number right there to remember. Is 0.707.
Okay, where does 707 come from? What? Why is that the number that's used?
Yeah, so that's a very good question. So 0.707, actually, if we were to use a little bit of calculus, or it's actually calculus in here, that's going to be the area underneath the line. And so it just happens that 0.707, and we could calculate it, but it's actually all the area underneath this line, which gives you an average of 0.707.
Okay.
So, and that's going to be of your peak voltage. So whatever your peak is, so we talked about peak to peak, which is your positive all the way from your positive to your negative, right? That's going to be from this to here. That's your peak to peak. Your peak to voltage is going to be from the zero line to one of the peaks. That's the 0.707 times that number is what we want.
Okay.
And that will give you voltage RMS. Another place where we see that, to kind of bring that back to real life, is at the AC high pots that we have. that will give you a peak-to-peak voltage. What you'll see is you'll actually see a meter, and it's been a while since I've seen one. Maybe someone else can voice up, but when we're doing a high pot, what you'll see is you'll see the meter, you'll see this gauge going back and forth, and that's just going from one peak to the next peak. So you'll see it go all the way max one number, it'll go all the way up through 0, and then it'll go all the way max to the other side, and it'll just keep doing that. That's not the voltage that we want to test to. We want to test to the voltage RMS. So that's how we get to that 0.707.
Okay.
Nice job. Okay, so we'll go to the next question here. This is, again, it's another series circuit. It may not look like it, but we have to remember that all these little circles that you see, these are just meters. So Darren, we have you on?
Yeah, I'm here, Matt.
All right, so maybe you can help us out with this one. So again, it's asking for what is the total resistance of the circuit?
So let's see. Well, so you got V2 at 4 ohms, or actually that would be what, A1? So between A2 and 3, you've got 3 ohms, and then you've got 6 ohms. So
okay.
if I'm looking at that, you're going to have 13 ohms is going to be your total resistance.
Excellent. You're right. So again, we just add them all up and we get our 13 ohms. And for any series circuit, doesn't matter how the series circuit is, doesn't matter all these different meters in there. And that's why they give you this question, because all these meters, it kind of confuses you, right? You don't know, well, maybe this is a parallel circuit because of these things that are going on. Those are just meters. So the circuit itself is just, come back over to another color. It's just this line here. That's going to be our series circuit. And you're absolutely right. You just add those up. Now,
Yeah, because
what if I were
kind of throwing me off, Matt? Looking at the V2 and the V3 was, is that going to be parallel or series?
Yeah,
right.
that's
what you're right. So that what you would look at is like this voltmeter right here. The voltmeter itself is connected in parallel with the resistor, but it's not really part of the circuit. So very good point. And I'm glad that you caught up on it. I think they were trying to trip you up a little bit, but you didn't fall for it. So nice job.
I thought you were trying to trip me up.
Oh, come on now. I don't do that. Okay, so let me ask you this. So now we've got our voltage and we've got our resistance. What if the question were, what is our current of the circuit?
You got me on that one.
Hey Matt,
Okay,
this
so
is Tim.
again,
Where are you getting the voltage? All I see is the resistance.
You're right. They didn't give us the voltage.
You are trying to trick me. I see how you are, Matt.
I was. Okay, so let's say that we have 260 volts. So if we have 260 volts.
So it'd be 260 times 13, right?
Okay, so what we want to do is we want to use Ohm's law again, right? So we'll write it, that's what we have up here, V equals IR. So we know what our voltage is, we have 260. We don't know what our current is, but we do know what our resistance is. So we have I times, you just told me 13 ohms here. So what we actually want to do is we want to divide. So it's going to be 260 ohms divided by 13.
20
amps. Exactly correct. So if you just kind of write it out and you think about, okay, what is it that I have? In this case, we had voltage, we had our resistance. Well, we got to get to our I. And so to get that, if you remember like first or second NETA at night, we talked about the Indian and the eagle and the rabbit. If you have to, go back to those, but this equation is given on the equation sheet as well. Okay, here's another series circuit. This time it's asking for current. So Tim, what you got?
I just got off another 12-hour day. That's what I got, Matt.
All right. So we'll do the same.
Yeah, first things is, of course, you add up your resistance, which would be your 4 and your 5 ohms, which would be 9 ohms would be your total. And then it's asking for current. So I have 9 volts and I have 9 ohms. So I would have, oh, wait a minute. No, it's asking for the resistance of the 5 ohm resistor. It's not asking for the total.
What is the current in the 5 ohm resistor?
Yeah, so your current on a series circuit is the same throughout the whole circuit, right? So yeah, it's 1 amp.
Exactly right. So that's the other question where they could trip everybody up. And again, you guys are way smarter than this. You guys have, of course, Tim, Toby, and they off the top of their head, which is awesome. That what you have to know on this question is that anytime you have a series circuit, you're going to get the same amount of current. Doesn't matter if that current is going to be at the forward part, between the resistors, after the resistors. Anywhere in that series circuit, you're going to have the same amount of current. So the current going through this resistor is going to be 1 amp. The current going through this resistor is going to be 1 amp. So that's the other thing that you need to know. That's not going to be part of an equation sheet. Okay, so this is a little bit different. This is kind of a fun question. It's a little bit more advanced here. So this one here, what it's asking for is what is the reading of the voltmeter on V1? So the first thing that we have to do is we have to kind of pull everything that we just pulled together from the previous question. So on the last question, first of all, what we can do is we know that we have an 80 volt drop across this resistor here. So if we know we have voltage, we have resistance, so let's calculate our current coming through that resistor. So I is equal to E over R, or 80 volts divided by 20, which is 4 amps. Now, since we know that we have 4 amps coming through this resistor, and using the theory that Tim just provided us, we know that we have 4 amps everywhere in this circuit. So we know we got 4 amps going through where V1 is connected. Now we know our current, we know our resistance. So if voltage is equal to our current times our resistance, we have 4 amps times 40 ohms, or 160 volts, is our voltage drop across V1. So the next question that they could ask is, okay, well, what is our voltage of the power supply? Anybody want to take that one on?
Would it be
240?
I'm sorry, say that one more time.
Would it be 240?
Yes, exactly correct. So what we do know, and we talked about this again in the past, was Kirchhoff's voltage law. So basically what we have is that all your voltages, if you come up around this, all your voltages have to add up to one another. So if we come across here, we said that we had 160. And then we come across and we know that we got 80. Come back and we got the power supply. So we know that we're going to have 240 volts. So we know this, if we bring it again back to the real world, we see this all the time when we're doing millivolt drops across the circuit. Millivolt drops, we'll start at one side, we'll go all the way up and around, and we'll come back to our original point, and we're going to see that all those are going to add up to that one voltage. And that's all that this is. This, you can think of this V1 and V2, all they're doing is millivolt drops or voltage drops across each one of those resistors. Same thing that we do all the time.
Hey, Matt, this is Toby. One quick one.
Yeah.
One quick one on that one. And you're absolutely right, of course. Just for some reason, I thought about it a completely different way, and I wanted to bring it up so guys could think about this too. I know that I have 60 ohms total in the circuit, series circuit. I can read it right there, 60 ohms. And I know, we figured out at the beginning, we're pushing 4 amps through 60 ohms. Just using Ohm's law right there, you can come up with 240 volts.
Awesome. That you're right. There's a lot more ways to try and figure these out. And so what you did was IR. The current we said was I don't remember what we said, 4, and we know that our total resistance is 60, 240 volts, and that's a good check too. So because we have all these different parameters, we can go back and check and make sure that we have that right answer. So Ethan, what if I wanted to know what the power was on this, how much power the circuit was drawing? How would I go about that?
To get the power, so you've got the current of 4 amps, obviously, and then total voltage 240. So you would just multiply those two together, which would get you 240 times 4. It's let me use a calculator. Hold on. So you get 960 watts.
960 watts, exactly correct. And so there's a lot of, as you can see, like this one pretty simple little drawing here, they were able to ask a whole bunch of questions. But if you break it down into the simple things, right? Current, voltage, and resistance, there's really nothing that we can't go ahead and solve. So nice job. This is one of the more difficult circuits that we had.
What if they asked for the answer in kilowatts?
Oh, very good question. Anybody want to take that one on?
Would it be 0.96 kilowatts?
Yeah,
yes, sir.
Exactly correct. So, and I highly recommend that you guys, if you don't understand how to convert things from watts to kilowatts to megawatts, milliwatts, same thing with current, right? You can have milliamps, amps, kiloamps. You know, we should make sure that we fully understand those. You know, what are the empirical units? Watts, obviously, is going to be multiplied times 1. Kilowatts is 1,000. Megawatts would be 1,000,000. Those are all types of things that probably wouldn't be bad for us to maybe on one of these future NETA nights to go over that, because there will be a lot of questions about that, or being able to use those different conversions on the NETA exam. Things that we should know every day. We do that when we're converting our ohms on our data sheets.
I'll say one other thing, Matt, is that sometimes that's part of the NETA exam too, guys. Read the question. They might ask, they might ask it in a way that says, how many kilowatts are drawn by how many kilowatts total in this circuit? And then you look, and they'll have 960 kilowatts. So if you do the math and you come out with 960 watts, and then you quickly start scanning the answers, and I bet you that 960 kilowatts is going to be A, and somewhere down like C or D is going to be 0.96 kilowatts. So you got to watch your units, and you got to read the question, because they will trip you up that way. It's not like they're trying to trip us up, but they're checking attention to detail, because our day-to-day lives as technicians, those are the details that we deal with, units and converting things. So they're testing that. And so I'd highly advise you to, even if you got to read the question 2 or 3 times, make sure you're dealing in the same units that they are.
Yeah, thanks a lot, Toby, because that is extremely important. You're absolutely correct. We'll bring that up maybe in another NETA at night if you guys want. Just shoot me an email if you guys don't understand all that. Here's another circuit. I'll go ahead and I guess who we got? Darren, you want to take this one on? So if the voltmeter V1 is equal to 3 volts and V2 is equal to 4 volts, what's the potential drop across R3?
Would be
So if the voltmeter V1 reads 3, the voltmeter reads
7 minus 12.
So 5.
Okay, so how did we come across to that?
So 3 plus 4 is 7, and then you've got a 12-volt system already. So your R3's got to equal 5 to equal the 12 volts.
Is what is being put on.
Exactly. So it's just series circuit, right? And so we know that the voltage drops have to equal one another, and so that's how we get it. So let me ask you this.
And you can
So
think
now
about
we know
that one. Wally's sitting right next to me.
Oh, you got a big cheater, pumpkin eater. Okay, so let's say we had 12 volts. Let's say we had our current was equal to, let's say, 0.5 amps. Yeah, 0.5 amps. What is our power? This time, Darren, without Wally's support.
What? So 0.5 times 12. So hold on, I gotta get out my calculator. I know.
He's already got his shoes off.
6?
Yeah, that's okay. Okay, so our power is equal to
So 0.5 times 12, right?
Right.
Equals 6.
6. What are the units?
So we got 12 volts. So, 6 watts.
6 watts. Right. So remember, when we're talking about power itself, real power is going to be measured in watts. Reactive power is the kVARs, kilovolt or kilowatts, kilovolts amps reactive. It's going to be kVAR or volts amps reactive, one or the other. This is just the thousands, like Toby was talking about before. Real power is in kW, and that's what we calculated here, and that's that power equation. And then we have the apparent power, which is in kVA. And we talked about that previous, and in future, maybe next time, we'll talk about power. We'll do a lot of power equations that deal with those. Okay, we're running out of time here. I would like to get to maybe a parallel circuit, if we could. And we could hit this again next time, but let's do a parallel circuit. So here's the first one. What we have here is that we got a parallel circuit. You guys can see that because we got 2 lines, right? We got this loop, and then we got this loop. So we got multiple loops, so it's a parallel circuit. So the question is, actually I erased the question. Okay, so what we really want to know is how much voltage is across V1 and how much voltage is across V2. Ethan, you want to take this one?
Sure. I'm not very proficient in parallel circuits, but shouldn't it be so the voltage is the same across both. So in a parallel circuit, so V1 and V2 should both read 6, I believe.
You're absolutely correct. So that's the other thing that they're going to try and trip you up on. So when we talk about a series circuit, we had the same current going all the way through that single loop. It's different with a parallel circuit. With a parallel circuit, all of your parallel loops, so we got this loop here and we got this loop here, those are always going to be identical to whatever our source voltage is. So now we know that we got 6 volts across this loop, and we got 6 volts coming across this resistor here. It's always going to be the same. So great job pulling that in. I know I kind of put you on the spot there. So if we know that, then how much current, this could be a follow-up question. How much current, if we put a meter here, how much current is going through this resistor, this 5 ohm resistor? Toby, you want to help us out?
Absolutely. Using Ohm's law, we know that 6 volts is applied across that resistor. We know the resistor is 5 ohms, so if I want to solve for current,
you're going to get a crazy
all we got to do is 6,
yeah,
6 divided by 5. I guess I could pull up the calculator.
Yeah, we'll just call it 6/5. Yeah, we'll call it 6/5 there. So we got 6/5 is amps are coming down through here.
Yeah.
And so now the second question could be, well, how much current is coming down through our 10 amp resistor? And it's going to be the same thing. So I'm going to call this one I2. I1 is going to be the exact same approach. We know that we've got 6 volts. and we've got 10 ohms, and so it's going to be 6/10. Of course, I got the easy one. So now really the question is, what is our total current coming out of the system? And so that's another piece of theory that you're going to have to understand. And this goes to Kirchhoff's current law that we talked about, some weeks back. Basically, what Kirchhoff's current law says is that the current going into a node, and a node is anytime we have an intersecting point like this, the current coming into that node has to equal the currents going out of the node. So in this instance, we've got the current coming in, and then we got a current coming out to V2, and we got a current coming down to V1. So if I say that my total current is equal to I1 plus I2, and then of course we're going to get a crazy number. It's going to be that 6/5 plus the 6/10.
It's 1.8.
And so basically what you're going to see here is you're going to see 18/10. I think that I did that right.
Yeah.
18/10, 1.8 amps is going to be our total current that is coming out of our system. And they could ask you this in many different ways. They could actually tell you that you've got 1.8 amps here, and that you've got 0.8 amps coming down this way, and what is this current coming over? And so there's many different ways they can ask you this. But again, if you just kind of think about where your currents are and where your voltages are, you can calculate if you got your empirical information, you can calculate all the other ones. So I highly recommend just taking a step back, drawing up your drawing, and thinking about exactly what it is that they're asking for. But those are the main things, the main concepts that you have to know for an equation like that. That voltages in parallel are identical in a parallel circuit, and that the voltages going into, or currents going into a node, have to equal your currents coming out of a node. So here's another question here, and I know that we're about to the end of our 30 minutes, but Darren, how about this question? If we've got a voltage drop across R1, the 3 ohm resistor, we got a R2, which is 6 ohms, and we got a power supply that's 10 volts. What is our voltage drop across this R1 resistor?
Voltage of 10.
Hold on that. So
Okay, voltage of 10.
it got voltage of 10.
And you got 3 ohms.
So this is kind of drawn almost a little bit crazy because of just the way that they put it. So you
So,
could think of this the same as what we just had.
So 10. So it's going to be hold on. God dang it.
Remember, Darren, he's not asking,
3.33.
he's not asking
what
you
we're
for the
gonna
current,
do-
but he's asking you for the voltage drop.
Yeah, the voltage. What do we have for voltage across this resistor here, this R1?
Oh, you still got 10 volts.
10 volts, exactly. So it might be drawn a little bit crazy, but again, as long as you recognize that it's a parallel circuit, right? We got 2 loops once again, so we got a parallel circuit. Voltages in parallel are always going to be the same. So we're going to have 10 volts across R1 and 10 volts across R2. Now, so we know we got our voltages across there, and then we could do the same thing. Okay, well, what is our currents? If they gave us our resistances, and so they could say, well, what is our total current coming out of the battery here? Now, you can calculate that in several different ways. One is we could calculate the current coming down this way, and we call that I2. We call the resistance or current coming down R1, and we'll call that I1, and then we add them up together, I1 plus I2. Or the other way to do it, which is a little bit quicker, is we could calculate what our total resistance is and draw this into a series circuit, an equivalent. We call it an equivalent circuit, which would have just one resistor, and we'll call that REQ, equivalent resistance. So how do we get to this equivalent resistance? Toby.
I was going to say, Matt, I think I want to argue with you. Doing the current's much easier than doing the reciprocal of the resistors.
Okay. I'm just trying to demonstrate that. You're probably right. But I want the guys, he's absolutely right. We'll do that one in a second as a check, but how would we calculate it if we just wanted to go this route?
Yeah, I agree with Tim on this one, but okay, well, cool. You got to know the equation for parallel resistors, and I think, if I'm not mistaken, that equation is actually on the data or the equation sheet. Is that right, Matt?
No, it is not, and that's why I wanted to bring this up, because it's not one of the equations.
Oh, okay. I'm wrong about that then. Okay, so
well,
it's
I have it right here.
Yeah, you're right. I don't see it on there.
Yeah, it's not on here.
Yeah, okay. Sweet. All right, well, what that equation is for parallel resistors is 1 divided by 1 on the lower side, 1 divided by R1 plus 1 divided by R2, and that would continue, for however many parallel legs you had. Now remember, if they throw 2 resistors in the same leg, then you got to add that in series, and that's your parallel leg resistance. So another little curveball they could throw you, but that's the equation. So you just plug that in there, and you get your equivalent resistance, and you can just figure your current and voltage using Ohm's law.
Right. So this is probably as difficult as it gets, guys. If you can calculate the resistances in parallel using this format, and sometimes you don't have all this information, and Tim's right, because they gave us our voltages across, the voltage drops across each one of these, it's easy for us. Okay, this is this amount, this amount, we just add them up. It's not always that simple. Maybe you don't have all those resistances, so it makes it a lot more difficult. Perhaps you don't have the value of R2 or something, and so you got to think about, okay, well, how do we do it? The other way to do, if you only have 2 resistors in parallel, you could also do your equivalent resistance, which may be a little bit easier with only 2, and it only works with 2 different resistors, is what's called product over the sum. So you can do R1 times R2 divided by R1 plus R2. And that's actually how I would do it. But what you really have to know is the equation that Toby gave you was and we call that the reciprocal of the reciprocal, or the sum of the reciprocal, the reciprocal of the sum of the reciprocals, which is kind of hard to say actually. But you can do product over sum. So what we have is we've got 3 ohms and 6 ohms. So 3 times 6 over 3 plus 6. And so we'll have 18 divided by 9 is equal to 2 ohms. And now that we know what our total equivalent resistor is, and we could write that right here. So now we know that our current was, we knew what our voltage was, 10 ohms. We know that we had 10 volts, and we have 2 ohms. So we know that our current is 5 amps. And again, if you understand this, and I know that we went by it a little bit quicker, and next time we'll start off with parallel circuits, but if you can understand how to come up with your equivalent resistance and go through there, then it makes it a lot easier. Now, going back to the way that Tim was talking about, which is very valid too. So what we know, just like we did in the previous question, we can calculate the current through each resistor. So here we know, we know that if we got 10 volts coming across this resistor and 10 coming across this one, and again, we know that current, we know that our current is equal to our voltage divided by our resistance. So we've got 10 divided by 3, and we've got 10 divided by, 6. So now all of a sudden, is that going to come out right? 20 divided by 6 plus 10 divided by 6. So we've got 30 divided by 6, which equals 5 ohms. So we get to that same, 5 amps. We get to that same answer using a different method. And you're right, Tim, your way was a lot quicker and easier than ours. But you guys have to understand how to do this, because sometimes things don't fit. And I promise you, when you take your NETA exam, they're going to throw these little nuances in there to make you think. It's not always going to be as simple as, Ohm's law. I mean, anybody can answer an Ohm's law if you go in there. What they want to try and induce is the thought behind it. If you fully understand it, or if you're just memorizing the equation and trying to get by with that, having a full understanding is going to take you guys a lot further and way beyond the NETA exam. This is stuff that we use every single day, whether you know it or not. If you're doing an insulation resistance test, if you're doing, a ductoring, we know what voltage we're inserting, we know what our resistance was given, or we know what current, right? If you have a 10 amp ductor, or if you're measuring at 1,000 volts and you get a resistance, we should be able to very quickly come up with what our actual current was coming through that circuit, or what our resistance was through that circuit, or voltage. So we'll stop here. That was about our 30-minute point. We went a little bit over. We'll pick up from here on the next one. But hopefully this gave you guys a little bit of an understanding. Certainly appreciate the feedback and the participation. Everybody did a great job. And I didn't look to see if there was somebody else on here. So if I missed somebody that was on here, then I definitely apologize. But we'll go through real quick. Does anybody have any questions or anything before we take off?
Hey, Matt, this is Darren. Hey, I appreciate this because Jason put out that he wants me to understand parallel and series circuits to do on my next tech topic. So this helped me out a lot, and I appreciate it.
Yeah, no problem. I'm happy to help. And if you want to go over this a little bit more before we get to you give that training, then certainly hit me up. And next week or next NETA, then we'll pick up on parallel circuits so that you have a little bit better understanding of that. I'm glad that he's given that to you.
Hey, Matt, this is Tim. I noticed in your formulas that you had V for voltage instead of the usual E for electromotive force. Is that something that's changing on the NETA test that I don't know about, or?
I've always used E as well. And this is actually a cutout from the exam. The equation sheet from NETA. And so I've seen it both ways, but they use V, and I think that you probably saw that I was using E before, but that's a very good point. So when you get to the exam, guys, typically what you'll see is, if I go back here, the way that I was taught, not to say that it was right or wrong or anything, but I remember power, doggone it, power equals pi, or current times voltage. And voltage was, like Tim was saying, was electromotive force, which was voltage. And so that's how I remembered it. And then I also remembered Ohm's law was E equals IR. Here they give you voltage as a V. Same thing up here, PIV. So they're interchangeable. If you get to the exam and you're like, what's going on with this? Maybe think about that they could be written both ways, either P equals IE or P equals IV. And voltage equals IR, or written as a V or an E. Great point out there, Tim.
Does this mean we're going to make the I's the A's next?
Probably. We just assign whatever damn letter.
Sons to bitches.
Just when hey, I'm still trying to figure out hole flow and electron flow. So I don't know. And I just blew everybody's mind. They're like, what? Whoa, what? I'd like to give a class on that, but I still don't understand it.
I think the easiest way that I've learned about hole flow and electron flow is they're virtually the same thing. It's that the electrons are flowing in one way and the hole is flowing in the same pattern to replace the electron, because it's not just a one-for-one swap. There is a gap or a hole, so it's all flowing together. It's obviously much more complex than that, but that's the most simplistic way I've learned it, and I've helped people like understand it.
Hey, I'll gladly
right
take this
there,
one.
Ethan.
This is Toby.
What's
Hey, look,
that?
man. What the thing is when we're looking at a DC circuit and there's a positive and a minus on that, you're showing a battery in there or a voltage source of some sort. we like to calculate things from positive to negative, right? Well, in actuality, an electron current flows in a circuit from negative to positive because it's electrons, man. They are repelled by negative, they're attracted to positive. So for us, and the way we like to calculate things, we came up with that term whole flow, but in my opinion, it's completely ridiculous. It's just a convenient way for us to make up an excuse why we like to calculate things from plus to minus, when in actuality, the current is flowing from the negative terminal to the positive terminal.
I completely agree. I feel like just the addition of the concept of what whole flow is just makes it more complicated. You just need to understand that electrons flow from negative to positive, and then that's basically just that's just how it works. There's no other need for another system or formula or anything like that. But
yeah, it's an anomaly that, depending on who you talk to, I personally feel like somebody screwed up and they just came up with whole flow to kind of explain their mess up, kind of BS everybody. But yeah, you have it absolutely right. It creates a gap, so the gap goes backwards, whereas the electrons are repelled by the negative force and goes from negative to positive. That's how I like to think of it. I think that makes sense. And so anyway, okay, well, guys, I appreciate you guys jumping on board. I feel like we made a lot of progress. I will send out these notes, and we'll carry on from here. Maybe do one or two on series circuits next time, and then we'll jump right into the parallel circuits and go on from there. Certainly had a lot of good participation tonight, and appreciate that. And maybe we'll do this just a week from now so we can get you guys geared up for those that might want to take the October exam. So with that, I guess I'll see you guys later. Again, I appreciate it, and thanks for staying up late tonight with us.
Thanks, Matt, for doing it.
Yeah, thank you, Matt.
No problem. Thanks, guys.
Thanks, mister.
Yep. Have a good night, Tim. Get some rest.
Right.